So we're going to discuss Kirchhoff's voltage law in this video. Kirchhoff's voltage law is all about conservation of energy. Very often, as we discussed earlier, it is helpful to think of Kirchhoff's voltage law in an analogy to gravitational potential energy. This analogy is very, very useful. For example, let's consider a path among three cities, from Champaign to Bloomington, from Bloomington to Decatur, and then from Decatur back to Champaign. We can label with pluses and minuses the height differences, and then we can label as the height difference from Bloomington to Champaign, that is the height at Bloomington, the elevation at Bloomington minus the elevation Champaign as delta H1, and delta H2 for Bloomington to Decatur, and delta H3 for Decatur to Champaign. Then we can add delta H1 plus delta H2 plus delta H3, and we know that since we've gone a full circle, the height differences should add up to 0. Okay, provided that all the height differences are in the same direction. So we'll label them all as height rises. So the height rise is 59 if you walk from Urbana-Champaign to Bloomington, 59 feet. And then we'll add the height rise from Bloomington to Decatur. But notice that it's actually a drop when you look at it. So therefore, it's going to be a negative number. The height rise is a negative number, and it's the same thing as a height drop. That height drop is 115 feet, or we can call it a height rise of negative 115 feet. And then from Decatur to Champaign, there is another height rise, elevation rise, of 56 feet. Okay, so 59 feet plus negative 115 feet plus 56 adds up to 0. That should come as no surprise if we figure out where these elevation differences came from. From Urbana-Champaign to Bloomington, we calculated it as 797 minus 738. Then the height rise from Bloomington to Decatur, we calculated as the height at Decatur, the elevation at Decatur, minus the elevation in Bloomington, which was 682 minus 797. And then we added the height rise, or the elevation difference, going from Decatur to Urbana-Champaign, as 738 minus 682. Alright, so there's something to notice about this, is that every number in this equation appears twice, once as positive. For example, there is positive 797, and then in the sum there is negative 797 because it serves as a reference point. There's negative 738, positive 682, and negative 682. So whatever we add, we at some point subtract. So it should come as no surprise that the numbers add up to 0. Incidentally, if we added another point to the path, the same logic would apply. Or if we changed polarity of one of the height differences. For example, if delta H1, we labeled it differently. We labeled negative at the Bloomington and positive at Urbana-Champaign. What we would mean then by delta H1 is the height rise from Bloomington to Champaign, or alternatively the height drop from Urbana-Champaign to Bloomington. That new delta H1 would have the opposite sign of the original delta H1 that we had. And here we have it in different color. So it would be delta H1, we could write it as delta H1 minus delta H2 minus delta H3 equals 0 if we now keep track of only height drops going from Urbana-Champaign, then from Bloomington to Decatur, and it would yield the same result. So the result is independent. The heights add up to, the height drops or height rises add up to 0, independent of the path taken. If we add another point to the path and go through that point instead of going directly from Decatur to Champaign, still all the height drops would be 0, or all the height rises, if we counted those, would be 0 as well. Alright, so let's look at the circuit example. Keeping track of voltage drop through the loop, we can figure out as we'll see, we can figure out later some missing voltages. But meanwhile, let's just see what the right equations would be. It's important to keep track of polarity in the equations, and each equation in a circuit will correspond to a certain path or a certain loop. So each equation is associated with a certain loop in the circuit. Alright, so let's look at the first equation. That's involving V1, V2, and V3. Okay, so if we go around the loop that involves V1, V2, and V3, we can see that we go up by V1, then we go down by V2, then we go down by V3, and we ended up at the same spot, at the bottom node. Okay, it would be helpful to blob the nodes if you have difficulty seeing that. So we finished the loop with V1, V2, V3, so A is correct. Equation B corresponds to a bigger loop that involves V1, V2, V5, and V6. And we can see that going up by V1, we end up at a certain node. Right now we can mark it as this dot. We end up somewhere there. You can also blob the whole node. There is an alternative path from the bottom to that node that goes through V6, V5, and V2. Right? You go up by V6, by V5, and by V2, and you end up in the same spot. So therefore, V2 or V6 plus V5 plus V2 should be equal to V1. So that checks out. Alright, there is a big loop that corresponds to equation C. It's a big loop, but it only has 3 elements. And again, starting at the bottom, we can start at the bottom, or we can start with V4. Starting at the bottom, we go up by V1 and go down by V4. So to this node that's just blobbed, and let's blob the other nodes too, just for convenience. To this node, from the bottom, we went up by V1 and then down by V4. The alternative path to this node is just going up by V6. Therefore, equation C checks out as well. Okay, looking at equation D, we can see that it's pretty much the same, involves the same elements as equation A, and it's just a rearrangement of the elements. But you can think of it differently. You can think you go up by V3 and go up by V2, and you end up at the same spot as if you went up just by V1. Okay, alright, so for loop E, you can see that if we go up from the bottom by V3, then we need to go down by V5 in order to end up the same way as if we just went up by V6. So E is wrong originally, but if you change the sign, if you just make this change, you can say, okay, up by V3, down by V5, same place as if you went up from the bottom by V6. Okay, so originally the wrong equation is E. Okay, so we can use KVL to obtain missing voltages in a circuit by making these equations that say add up to 0, right? Going through the loop and all the rises through the loop adding up to 0. Alright, so the unknowns here are V1, V2, and V6. And I'm not too happy that I put the question marks right in the elements. We don't know what these elements are, but just here it marks the fact that the voltages are unknown. This voltage is known, so I just erased the subscript and labeled it right on the circuit as 2 volts. This one I can label as 6 volts because it's given to me, and finally V2 is also given to me as just 1 volt. Sorry, not V2, V5, as just 1 volt. Okay, so V1, V2, and V6 are unknown. Let's find a loop that has only one unknown, and let's call it loop A. Okay, so loop A has one unknown, and we can go through the loop going up by 2 volts, dropping by 1 volt, dropping by that unknown, and that adds up to 0. Therefore, our unknown is just 1 volt. And you can just verify the math for yourself. Alright, now let's find another loop with just one unknown in it. Here only V2 is unknown. And if we start at the center blob node and say we go up by V2, because we encounter minus first, so we know we're going up by V2, minus 6 plus 1 equals 0. Okay, so you have to you have to be careful the way you say go up or go down by a voltage, and that depends on how you labeled it with minus and plus. Alright, so V2 is just 5 volts because V2 minus 6 plus 1 equals 0. So V2 equals 5. So we just figured out what V2 is, and therefore it makes it easy for us to figure out what V1 is by using this other loop in the corner. And let's say we go up from this bottom node that we haven't blobbed before. If you have trouble with this, always blob the nodes first. Okay, so going up by V1, then going down by 5 volts, right? Then going down by 2 volts, we end up in the same node, which is 0. So the sum is 0, and therefore V1 equals 7 volts. Okay, and that's it. And we'll pick it up with KVL next time. Thank you.